So I listed a few key points that you guys have to pay attention. And I also included a table that would be really nice to it would take a while to kind of get a trend of how will each molecule, how each resonance will appear on the peaks. And we can practice that. And I can walk through some examples with you guys. So this integration number tells me that this hydrogen has 3 hydrogen on a carbon. And know that this has 3 hydrogen. This one has 3 hydrogen too. And from the peak, we saw that there's a triplet, n plus 1 equal to 3, n equal to 2. It means that there's 2 neighbor hydrogens. And that makes sense because one of the neighbor hydrogen is this CH2. And then for here, we have a hydrogen that's near the nitrogen, which de-shielded has a de-shield effect because nitrogen is electronegative. And n plus 1, this is 4 peaks, n equals to 3 neighbor hydrogen. And that one makes sense because on the side there's 3 hydrogens. This side as well, 3 hydrogens. And the integration number is 2, which matches up with our expectation. And then isobutyl acetates. Here's a nice rule you guys can follow. In between 4 and 3 ppm, you can almost assume that there's an ester. And that hydrogen is corresponding to that one. And you can look at the chart here between 3 and 4. We should kind of see that there's an ester hydrogen. Or a more closer one. Is there somewhere close to that? But this one too. Yeah, it's between 3.5 to 6, which is in the range. And it looks like this, R, O, and this is our carbon. It means this hydrogen. And we have 2 of them. And this peak right here, the 3, is singlet. It means there's no n plus 1 equals to 1, and n is 0. There's no neighbor hydrogens. And the only one here we can see is this one. Because remember, this is just a carbon. There's no hydrogens here. And then we also have a 6. Oh, by the way, here's 1. Integration is 1, which means there's only 1 hydrogen, which is this one. And let's see how many neighbor hydrogens it got. N plus 1 is equal to, we have 6, 7, 8. And this is a multiplets, which is pretty iconic for isobutyl. So whenever you see a multiplet, n is around 2, it means that there's an isobutyl group. And then for 1, it's corresponding to the 6 hydrogens here. Because there's a symmetry right here. So that's why 3 plus 3 is 6. And it's a doublet because it means that there's a carbon. That there's a neighbor hydrogen, which is the one in the center. And I will let you guys work through this. Can anyone tell me which hydrogen that this one should correspond to? Yep, it's this one. And it's a triplet. That makes sense because m plus 1 is equal to 3 and is equal to 2. There's 2 neighbor hydrogens. That proves it. How about this one? There's a de-shielding effect. This one is kind of tricky. And the second carbon on the right of ester. Yes, this one. And we can confirm it from the table. Let me erase this. What we are looking for is the carbon, the alpha carbon, which is this one. And it's around 3 to 2. Then what do we have? Around 2. So yeah, it's this one. And n plus 1 equals to 4 and n equals to 3. 3 neighbor hydrogens. That makes sense. How about this one? It has an n plus 1 of 4 and equals 3. But that one's more shielded, which means it has its neighbors doesn't have a strong magnetic field or electronegative. But yeah, it's kind of upshielded, and we can correspond this to this one, which has a integration number of 2 hydrogens, 4 hydrogens. Actually, sorry, n is equal to 3, so there's 3 hydrogens. And then now we just have to decide which one is which. This one is more shielded, which means it's far away from the electronegative carbon atoms. This one is more de-shielded, which means it's closer to the ester group. And this one is farther away, so that's why it's more shielded. How about this one? Benzenes. Benzenes are usually around 8 to 6. We have 1 carbon. we have another carbon. And we can see that there's a nice symmetry going on here. So that's why we have an integration of 2. And it's a doublet, plus 1 equals to 2, and equals to 1. And that makes sense because there's only one neighbor hydrogen, There's no hydrogens here, keep in mind. And the 6 comes from that. And around 2.2 ppm. We go back to the table. Around 2.2, there should be one that's noting that a hydrogen is attached to a double bond. Let's see, can we find it or not? And it seems like aromatic CH, yeah, right here. Aromatic CH means there's an aromatic ring, there's a carbon, and a hydrogen right here. This is what it means. So aromatic 3 and 3, that's 6. And plus 1, this is singlet, and it's equal to 0. And there's no neighboring hydrogens because one of the carbon that's next to it, it doesn't have any hydrogens. So it's empty. And then this one is the last one, NH2. And one note, around 9 to 8 ppm, there will be a amide hydrogen, which is this one. This one is the benzene ring. Corresponding to the 3 hydrogens here. And same as before, the 6 corresponds to this 6 hydrogens. And lastly, the hydrogens near the carbonyl we mentioned before is around 2. And the integration is number 3. How about this one? Can someone tell me which one is this? Right. There's 2 electronegative sites here, which deshielded the hydrogen to -4, and singlet because there's no nearby hydrogens. And as I mentioned before, this one is this, and the rest should be easy. This one is this, and the rings. And here's a question from the 2016 theory quiz. What will be the splitting pattern of the resonance or for the proton shown in bold? So this one. The splitting pattern basically tells you E septets n plus 1 equals to 7 and equal to 6. Yep, because there's only 6 nearby hydrogens, which is this 3. And then n plus 1 septet. And the next one. To which of the following compound does the above proton NMR spectrum shows? And here's a nice thing you guys can do. Whenever you see 1.5, multiply by 2. And since you multiply everything by 2, this one has to be multiplied by 2 as well. So this will be, the integration number will be 2 and 3. And continue. Hydrogens on the non-carbons. So the question didn't say it, but usually we use CDC. It was CD. Yeah, whatever that is. The solvent, CDCl3, I believe. Yeah, it was CDCl3. The deuterium here can exchange with exchangeable protons, like the hydrogen bonds here. Those hydrogens are exchangeable with the solvents. So any hydrogen that is exchangeable will not show up on the spectrum. D, okay. So let's see, it's around 3.5 to 6, which means it's very likely that it's an ester. So we can cross this out, we can cross this out. And just to make sure that if there's a symmetry right here, and we have 9 hydrogens. So we should kind of expect that there should be a like somewhere here, and integration number is 9. But it's not here, so we can cross B out. And for A, there's 1, 2, there should be 3 peaks. But here we only see 2, so we can cross this out. And D is correct, I agree, because 2. And remember we said that for ester, it's around 3.5 to 6. And we multiply by 2, we have 3 hydrogens, and that makes sense. This is this one. And singlets, which means there's no nearby hydrogens, which is true. And for A, it's in between 2 electronegative atoms. So that's why the effect, the de-shielding effect is stronger than the methyl group here. And the integration number is 2. So that makes sense. Which means the following compound, it will be D. And redraw your structure. I will do it here. And then I kind of explained it before. This is B. This is A. And I just want you to draw the assign the peaks instead of giving explanations. But if you want to explain it, then you can say that peak A is more de-shielded than B, so that's why it's on the left. So here's the thing about OH and amide. So because of how NMR determines the integration number, whenever you see like a 1.5 or 1.3, you want it to a integer number. Everything here is multiple. So to get a full number, you actually have to multiply everything by 2. And back to the question, like about hydrogen bonding. We want hydrogens that's dissociable. And then we have deuterium, CdCl3. We want the deuterium and the hydrogens being exchangeable. This one's really basic, which means it wants to hold on to the hydrogen. And the hydrogen on the ethanol, it's kind of like a known fact that this is dissociable. So if this one is being replaced with the CdCl3, DO, we got D here, and that's not a peak because it only detects hydrogens instead of its isotopes. And for acetone, the ppm is around 10. This one is not dissociable. It's connected to the central carbon really nicely. And then carboxylic acids is normally the peak will be really low. Peak is very weak. It does show up, but it's very weak. It's because of this interactions well known to the carboxylic acid, the internal hydrogen bonds. It takes energy to break this bond, and so that's why some of them will be left there and being detected. And the ppm is around 12. Very distorted. So typically, whenever you see a alcohol or amine, these two are exchangeable. But for carbonyls, they do show up. No peak. And that's the idea here.
There's no peaks for amines either.
There's peaks for there's no peaks for amine too.
Okay, thank you.
Yeah. Even though I said that it's basic, but somehow it doesn't show up. Sorry, I don't have a better explanation than this. And let's go back to the slides. Okay, that will be our last question. Which of the structure corresponds to the NMR spectrum shown above? So we have compound 1, 2, 3, 4. We have this, 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 and this being different. I covered this up. And we also have a deviant, which is a methyl group sticking out of here. That's one of the variables. We also have different functional groups on the top. Everything else is the same. And then just judging by this information, which one is which? We can also have some information from the mechanism or the reaction that was being provided, which is heat. That means that we have some sort of attack. This is a nucleophile. And so that there's a electrophile. So maybe this will bring in and kick out the alkyl group. And we left with a OHCH3. And the one that's being kicked off, like there will be base coming in and grab this away. So this is also a heat that can be useful. And let me ask you guys one question. What should be the ppm of a carboxylic acid? Somewhere higher. It's actually around 12. And it's not showing up, so that means we don't have carboxylic acid. And we can eliminate answer choice 2. Let me annotate with the slide feature. And we don't have carboxylic, and we don't have carboxylic 2, so we don't have 1. It's 3, yes. And let me tell you that why it's not 4, because for 4 oxygen to the double bond in CH3, we should have the integration 3. But the integration of that one won't be this, because that one is for ester. No, that one is for, that one is for ester, and this one is not. And it's not on the spectrum. Spectrum. So we can eliminate 4. And then we can also try to assign peaks. So we have a structure of a benzene. And then we have our alcohol here. This is exchangeable, so it's not on spectrum. Or maybe because it's on the benzene, it somehow appeared. So if I were you, I would actually try to say that this one is C. Maybe it's a different color. C. And we have some sort of symmetry going on here. And now the only question is which one is A, which one is B? So A is more deshielded than B. And the closest atom to a deshielding effect is actually the hydroxyl group. So I would say that this is A. And this is B. And let me check that I got it correct or not. Yeah, I got it wrong. This one is actually A. Or B. This one's A. And the explanation to that so you guys can note this down. And the resonance EMF should be relatively easy. Oh, weird. But yeah. B, A. This one is more closer to the ester. So that one should be E. And that one should be F. And that one is D. E is the benzyl proton. F is closer to the ester. F is close to the ester. Yep. And that will be it. Amines are surely more polar than amines, yes. This can actually resonate. And that will become, oh, sorry, not from here. And that will become that will become an amine. And meanwhile, amine, we have H and H. We have a dipole moment here. We have dipole dipole moment here, but then it can also resonance. So that's why amide is more polar than amine. That's on the all the way at the beginning. Keep. I see. Increasing polarity. This is our amine. This is our amide. Yeah. Follow this one. Don't listen to me. But yeah. Amine should be more polar than amide. Yep. And before that, I will stop recording.